course, we'll talk about dynamics. Okay, so let's start. If there are any problem, you guys can just interrupt me and tell me through the message or your voice. Okay, so first, let's talk about this homework. Actually, I think this example is not very difficult. I think you guys can finish by yourself. But I will do the do we will do this together. Let's check the result. So now first I will read the problem. So you guys can just look at the picture. It said a four bar linkage, A B B C C D, and actually AD is another linkage, but it is fixed on the ground, so we can call that frame, right? So actually, you can find AB will have a rotation around the fixed point or axis A, and related body CD will have another rotation around the fixed point D, right? And actually, this slider, not slider, this linkage bar BC is not connected with the ground directly. Actually, it connects with AB at point B, and it's connected by uh, by here with another constraint with CD, right? So actually, this BC will have a complicated movement. We call that plane motion, which is the main topic of chapter 9, right? So AB rotates around the point A with a constant angular velocity omega equals 1 radian per second. And let us determine the velocity of point C and the angular velocity of DC at this moment. Actually, after our analysis of this whole mechanism, we will find actual AB and CD are two rigid bodies have a rotation around fixed point, right? So since omega equal 1 radians per second, so we can easily find actually uh, I will try to draw VB here, it should be along the horizontal. So this is VB. So we can write at VB at magnitude should equal omega times LAB. So I will change these centimeters into meters, right? So just times, let's write like this, LAB. So we have 1 radians per second plus
Point one.
0.1 what?
Yeah, 0.1.
Yeah,
Yeah,
and it should be 0.1
zero one
meter per
meter
second,
per
right?
second. Yeah, yeah,
Right? I think it very easy to understand, right? And
yeah,
we can find actually this direction of VB, it have an intersecting angle with direction BC with 45 degree, right? So here you can see this purple color actually it is VC, you know? Why we know VC should along this direction? Because actually point C also is a point on this CD, because this when AB rotates along this CW direction, there is a force along BC direction try to push CD around rotate around point D. So there will be, I'm sorry, this will be omega CD, which is let us determine the angular velocity of DC at this point. So actually, VC also should equal omega CD times LCD. So actually, right now, we don't know the magnitude of omega CD. We also don't know the length of LCD. So we should calculate this one and this one respectively, right? And through this linkage bar BC. We know actually it has a plane motion, and B and C is a 2 point on this rigid body which has plane motion. And we can use the theorem of projection method. Do you guys still remember? Actually, we can write so uh, at or from BC at BC, right? At linkage BC, we can use theorem of projection method. So we have VB times cosine 45 should equal VC cosine 0 because cosine 0 actually 1. So actually we can find here actually VC equal 0.1 times right. So this should we can just let it like this. We can also use like MATLAB. I will just use my cell phone, So we have, let's see, maybe you can use MATLAB, you can use your calculator. So now I will just use my cell phone to give this. So we have 0.1 times square root second, right? And divide divide second. Sorry. So let me do this again. So square root second equal over second equal. So it should equal what? I'm sorry. Let me try. So we can use this. MATLAB is quite powerful. I highly recommend that you guys should learn how to use this software. So we have 0.1 times squared root second. 0.5 over second. So we can write here 0.0707, right? So that's the value. So we can write here 0.0707 meters per second. So you guys can once again look at this expression. Actually, we have finished the first task. Determine the velocity of point C. We have its result here. And then the second task, we should know the angular velocity of DC, right? So actually omega CD is here. We just need to find the length of LCD from geometrical conditions here. So let me try. So if I draw a perpendicular added line here, so let's see ECH from here and here, you guys will know actually this will 20 centimeters, right? And this is the 45, so here should be 45. Then the length of CD, we can find it LCD times sine 45 will equal 20 centimeters. So LCD will just equal 20 uh, uh, divided times this. Actually, right? So you should pay attention to its units. Then we can use this and this. We will find actually omega CD equal what? 0.0707. And here, because this is centimeters, we should change it into meters. So just 0.2, right? And then we can use MATLAB once again to find the final result. So let me do that. So once again, we use 0.0707 over 0.2 over. So actually, I write this. I don't know how to write it in English. Uh, two to the power 0.5 actually is square root second, right? So the final result will be 0.25. So here should be no 0.25 rate per second. So actually these two results, if you guess have these two results, then your answer is correct, right? So I think that's all for this problem. It's not uh
Kaushik, can
what?
you again tell this one? BB cos 45 degree equal to BC. I can understand this.
Which one you don't understand? You don't know why length of LCD is this, right?
No, no, no. This one. BB cos 45 degree equal BC point one.
You see this equation, right?
Yeah, 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 yeah.
I think maybe I just will back to the last time what we have learned. This is the theorem of projection method. Let me put it this way. No, if you can just look at this, you can just look at this B and C, actually these 2 points on a raised body BC, which has a plane motion. So if we try to find the velocity of point C, so we can use B as the pole point. Do you still remember? Actually, we have VC equal pole velocity VB plus VCB, right?
Yeah,
Uh, do you guys still remember this expression, right? So
yeah,
if I can draw for you. So actually, I will change my pen's color to another. Let's see, it's green. So actually, we try to find the absolute velocity of point C. So actually should equal this element. This element is vector sum. So here should be VB, right? We also
yeah,
have VCB as velocity of this point relative rotation around the point B. But we know actually this VC always should be confirmed. It should at the diagonal position. So our VCB should be perpendicular to BC. So it should along this direction. So this should be VCB, right?
yeah,
That's what we have learned. So if we see, if we see this is expression one, uh, let us do this projection. We projection this vector equation to this direction BC, you know?
yeah,
So I mean, this direction B C means from B to C. Actually, this let me see. This direction I can give expression conceive one. So from B to C is a positive direction, right?
yeah,
So we can projection this whole vector equation onto this direction. So we just project from left to right part of this expression. I will write here. So you will find actually VC is on this direction. So it intersects angle to this direction conceive one actually is zero. So we can have VC times cosine zero and just write this equal sign. And then you can find VB. So this VB will parallel to this VB. So if this is 45, so here also is 45, right? So we can just write as VB times cosine 45, right? And you can find actually VCB is perpendicular to this direction. So when projection VCB onto this direction, it always be zero. So that's why our projection, our expression here is correct. So we call that this method is velocity projection method. Actually, we have talked about this last time. So today I just use this method directly. Maybe you don't remember that. So can you understand that now?
Yeah.
Okay. Oh, that's why, right? So that means if you know a rigid body like BC, which has a plane motion, and you know 2 points on this body, its absolute velocity and its intersect angle with this direction BC, so you can use this velocity projection method to quickly find another's value. So let's see, we know direction of VB, we know magnitude of VB, we know direction of VC, so we can quickly find magnitude of VC. Just use this projection method, right?
Yeah. This is BC cos 0 degree equal BB cos 45 degree, right?
Uh, uh, please see it again.
BC cos 0 degree equal BB cos 45 degree. That's
You see, VB times cosine 45 equal VC times cosine 0, right?
yeah. That's
Yeah, because cosine 0 just is 1, right? It's 1.
yeah. I know.
So actually,
BC
this is the
cause
C.
BC is 0 degree.
Yes, because BC is a rigid body which has plane motion, right? So because it has a plane motion, so we can select B as the pole point. So we have this expression, and then we can do this projection method, right? So maybe I come back to the page what we have learned last time. I will try to find that. So I think this is the page last time we talked about the velocity projection method. Maybe you guys just want to this PPT file, but I forgot to send you, right? So maybe I should send this file to you guys. Okay, I will send to you now, just in case I forgot that again, right? So just wait a minute. So let's say this chapter 9, and I will send you guys here, right? Uh, okay, I think that's all for this homeworks. And I think we just look one more example because this part is a little bit difficult. I only need you guys have impression is enough. So I will just discuss one more example from this chapter 9. Then all of us will move into the new chapter, chapter 10. So let's see, uh, try to follow me and understand what I'm talking about. So in a crank rod mechanism, so you can see we call that it a little bit similar to 曲柄滑块机构. So the radius of the wheel, let's see the radius of the wheel is R equal 15 centimeters. And N equals 60 RPM revolutions per minute, and OA equal also is also is 15 centimeters. So our task is to find omega b and alpha b of the wheel when this angle alpha equals 60 degree and OA perpendicular to this AB. So if here is 19 degree and here is perpendicular from one line to another, so it's quite easy to find here should be 30 degree, right? So if it have this, because when OA rotate around the point O along this CCW direction omega, and this magnitude omega we can find from this n. Do you guys still remember how to find the relationship between omega and n? So let me tell you in details. Because we know angular velocity omega has units with radians per second, right? And n its units is revolutions per revolutions per minute. So if n is this, we try to change n into omega, then we can know actually one revolution, its radians will be 2 pi, right? And 1 minute equals 60 seconds. So we will find actually we just need to use n times 2 pi over 60 seconds. Then you will find actually omega equal n pi over 30. That is how we find the relationship between omega and n, right? So actually just need to change its unit from RPM into radians per second, right? So let's see how to find the result of this problem. So first we should consider rod AB. So rod AB once again do not connect the frame directly. So actually it connects OA at point A, it connects this wheel at point B. So actually this linkage AB is another typical rigid body which has plane motion, right? And you guys can see, actually, we just talked about why this is the expression. It tells us the relationship between omega and n. So we have actually omega OA is 2 pi radians per second. So we can find the direction of VA. We also can find magnitude of VA here, right? So VA equal OA times omega. And here you should pay attention to its units. So here 15 centimeters. So we have 15 times 2 pi. So we have 30 pi centimeters per second. We should highly pay attention to its units problem. Then, because here we have a yellow wheel, so actually, in this kind of mechanism, we always think about that the force is from the direction of AB. So if OA rotates around point O along this CCW direction, it highly will has a force from A along BA direction. So this wheel will move from right to left. Actually, also have a CCW angular velocity. So we can assume that alpha b its angular acceleration also can be assumed along the same direction of omega b. So although we don't know omega b, we don't know alpha b, we only can assume its direction, but we will know actually VB must along this direction, right? So because the distance from the geometrical center of this wheel to the fixed ground will never change. It's always r equal 15 centimeters. So that means we know the direction of VB. So actually, because here is 30 degree, once again, we can just use a similar pattern as our homework. We just finished discussion, right? So actually, we can use the velocity projection method again. So we can find VB times cosine 30 equal VA equal what? 30 pi. So you can find actually VB equal, because it's 30 pi times, I'm sorry, uh, should be second. So it will just equal 20, maybe like this. So this is how we use the velocity projection method. Here we use another method. Actually, we have talked about the instantaneous velocity center. Do you guys still remember? So actually here A and B are 2 points on a rigid body AB, which has plane motion. So we know VA direction here, we know VB direction here. So we draw two dashed line. So one is perpendicular to direction of VA, another is perpendicular to direction of VB. So we will have intersect point. So actually this is instantaneous velocity center. Do you guys remember? So if we find this center, actually VA will also equal omega AB times LP1A, right? And our VB also equal omega AB times LP1B. Since we know the magnitude of VA from here, so we just use VA over LP1A, we can find omega AB. Then we can find length of P1B, then we can find magnitude of VB, right? So this we call the instantaneous velocity center method. And so P1 is the instantaneous velocity center of AB at this moment, at this position, right? So we will have this P1, and once again, P second is the instantaneous velocity center of the wheel. So you guys should know, we have talked about this. If a wheel with a pure rotation, we call that 纯滚动 at some fixed curve. Maybe it's a plain ground, maybe it's a curved ground. The contact point will always be the instantaneous velocity center of the wheel. So actually, here we can see this point B also is the point on the wheel. So we also have VB should equal omega B here times R. This R means the distance from B to the distance to the point P second. So if we can find VB, we just need to VB over R, we can find omega B, right? So you guys can find our omega AB, how to find length AP1. So if here is, because we know here is 90 degree, and let's see, OA is 55, right? And this is 30 degrees, then OB will be 30. And this length, AB, will be 30 times cosine 30. So here will be 15 times square root 3, right? Because we have 30 here times cosine 30, which is square root 3 over second. So here will be 15 times square root 3. And here is another rectangle triangle. So if there is 30, because this dashed line will perpendicular to the horizontal line, so here will be another 60, and here will be 30. right? So you guys can find, because this 30 degree, so here will be 30 times, and the length of P1A will just need this 30 square root 3 times cosine 30, which is another square root 3 over second. So that means this length will be, let me see, uh, 45. Am I right? So this will be 45. Let me check it. 30 times cosine 30 will be square root 3 over 2. So this will 3, and this will be 15. So the whole length will be 45 centimeters. That's length. So you guys can find AP1 VA over AP1. You know, this is 45, right? This is 45. So we have omega AB equal this result. So we just need to analysis all the information one by one. Then we will find a method to calculate, including omega AB. So you guys can just look at the picture here. Since we know the length P1B equals 30 times square root 3, so we will find actually VB VB also equal omega AB times uh, BP1, which is here we know omega AB 2 pi over 3 times BP1 we give here. So this is 30 square root 3. So it can finally equal what? Equal uh, so can you guys find it the same result? So actually here we use the velocity prediction method to find the magnitude of AB. Here actually we use the P1 is the instantaneous velocity center of AB. So we can find this, right? So once again, because we know VB also equal omega B times R, because P second also is the instantaneous velocity center of the wheel, right? So we will find actually omega B will equal VB. So we just use its result 20 square root 3 pi over R also is 15 centimeters, right? So we can find, we eliminate the file, we have and 4, so will be 3 radians per second. I hope you guys can understand this. So I will change another. So you will find VB actually 20 square root 3 pi centimeters per second. Just the same as we have calculated by ourselves, right? And the last second, so this page just tell us how to find its velocity, acceleration. Maybe it's a little difficult for you guys to understand, so I will try to explain this. But if you can totally have no idea what I'm talking about, it's fine. It's fine. I only need you guys have a little impression here is enough, right? So actually we know actually OA has a constant angular velocity. So the acceleration of point A will only have normal part. So this is omega squared times OA, which we have this result actually AA along this direction, just like this. So if we draw a AD line, so because alpha x 60, actually this is 60. You know, here is 60. And we should use the theorem of velocity composition, what we have learned. So we select point A as the pole point. So we can write AB equal AA plus ABA tau and ABAN. You know, ABA tau, right? ABA tau is, you can think about you are sitting on point A, you look at point B, you will find actually B around the fixed trajectory of circular path. Then this ABA tau will always perpendicular to AB, but maybe along this direction, maybe along this direction. So it's totally according to your assumption of its direction. So if we assume that alpha b along the same direction with omega b, so ABA tau will equal alpha b times LAB, right? So so its direction will along this direction. Another is ABAN. It's a normal line part of this ABA, right? It always equal because ABAN will always equal omega AB squared. We have its magnitude times LAB. So we know its magnitude, we know its direction. So here is we know the direction of AB, right? Because this point always have the constant distance to the ground, always be r. So AB will always along the horizontal direction. So that you will find from this vector equation, we just have two unknown quantities. So that means this can be resolved by this. So we can draw the vector diagram for accelerations, projecting the above equation onto BA. So here BA means from B to A, means means this direction is the positive direction. So we can do this by ourselves again. So you guys can look at this expression. So here should be 30. So we will find actually AB times cosine 30, right? Equal, we just draw the equal sign here. AA. So it's very convenient that actually AA is perpendicular to this AB, because here we know it is 90 degrees. So AA project on AB also 0. And ABA tau also is 0, right? So, and here 0, and ABAN times ABAN times cosine 30. Although we can do this projection, but it's invalid. You know, actually we will try to find this alpha b, you know, so we will try to find ABA tau, right? But if we just projection this vector equation on this direction, so actually ABN do not need us to find its magnitude. We know before the projection, we know its magnitude and direction. So this is useless. This is useless. So actually we can try to, I think, I'm sorry. Actually use this, not, I'm wrong. I will re-put it this way. Actually, here we only know the direction of AB, but we don't know the magnitude of AB. So we can just use this. We find AB actually is equal ABAN, right? AB actually its magnitude equal ABAN equal this, right? So the only thing is how how we can find alpha b, right? how we can find alpha b. So this time we can just find another axis to redo the projection method. Let me tell you guys, we can like just select the vertical line. Let's say it can see 1. So we can once again project expression 1 to conceive 1 here. So because when we give this direction, you can find actually AB perpendicular to this conceive 1. So we have 0 equal what? And AA, AA because this is 60, so it has 30-degree intersect from to this conceive 1. But its projection onto this conceive 1 will have minus part because it's direction here. So we have minus AA times cosine 30. And ABA tau actually here, this angle also is 30. So we will plus ABA tau, we write as alpha B times LAB times cosine 30. But its projection part will along the positive direction of conceive 1. So this is positive. Then this ABAN, this ABAN, if this is 30, so this is 60. So we only need to plus ABAN times cosine 60. So you guys can find at this expression all the things AA, LAB, ABN, all known. So we can use this expression and can find the magnitude of alpha B, right? That's how we find the final result. I hope you guys can understand this. So we use this projection. Maybe it's a little bit difficult for you guys to understand. So we use this projection can find AB, right? Then we can use another projection to find alpha B, right? So we can find alpha B. Actually, here it uses another conclusion. I will not put that in this way. Actually, I have told you guys we can just give a vertical direction conceive 1. We just need to projection this whole vector equation onto that axis. Then we can find A, B, A tau. Because A, B, A tau actually it equal alpha B times LAB. So we only need to use ABA tau over LAB, then we can find alpha B. Maybe I will just leave this to you guys. If you have interest in here, you can try to do this by yourself. Maybe you will find it's the same result from here. So actually it tells us consider wheel B, consider wheel B, its instantaneous velocity center is p second. We have used once. And this AB, we know its direction and its magnitude. So actually this AP second, it will equal omega AB, not square times R. And we also can find actually AB. Because we can write as AB equal a p second plus a b p second tau plus a b p second n. So it's quite complicated. So maybe you guys just need to have a basic impression here is enough. I think I should not introduce to you guys with in detail here. So actually we have another method do the projection, and we also can find alpha B, right? Uh, and, and actually here we find alpha AB. Okay, okay. I think that's all. That's all for this problem. It's quite difficult, quite complicated for you guys to understand. So I think maybe it is time for us to move into the new chapter. I think that's all for this chapter 9. Actually, I have sent this PPT file to you guys. If you like, you guys come back to this file, can read it. Actually, we have a lot of examples, but we don't discuss together. No, because it's too difficult, too complicated for you guys. So I will just leave it here. If you are interested in this, you can read it. If you have some problem, you can discuss with me in personal, right? So I think I will do not cover all the examples on these PPT files. Okay, so we don't have another homework from this chapter. I think it is time for us to move into the new chapter. I will just close this chapter. So let me do a short introduction here. So actually from the chapter 10, we'll move into the part third. Also is the final part of this whole course. We call that dynamics, you know? So the first part of this course, we have discussed some knowledge point of statics. Then the middle part we just finished after the learning of chapter 9, actually the kinetics, 运动学. And then the third part, which also is the final part of this course, we call that dynamics. Actually, in Chinese, we call that 动力学,动力学. So our first part, statics, do you guys still remember? Statics. We call that 静力学. Dynamic, kinematics. The middle part we just finished learning today, we call that 运动学. Here we are going to talk about the third part, dynamics, which is 动力学. Actually, the core knowledge point is the second law of Newton's. So we have F equal ma. I think you guys will have some impression of this very famous Newton second law, right? Because it tells us the relationship between force, F means force and A means acceleration. So we can give the body or the body system its information of kinematics. Maybe we also can find some information from statics. Then use this expression, we can link force and kinematics together, right? So that's why we call that this part is dynamics. So let's see some brief introduction here. So first, the subject of dynamics is the relation between the mechanical motion of a material body, because a body have different material will have a different mass, right? Because we know mass equal rho weight, this volume, and this is 密度, how to say its English, density, right? Density times volume. So different material will have different density, and the same value of different material will have different mass. And this we will continue to do this brief introduction, but it is time for us to have a short break. So we will restart our class today at 11:10. So please, all you guys have a rest. Okay?
Okay, Lash.
Okay.
Okay, Arjun.
Okay, Ren, our time is up. Let's continue our class today. So we will start to talk about the dynamics. So before we do some normal learning, we should know this brief introduction. So the subject of dynamics is the relation between the mechanical motion of a material body and the force acting on it, right? So here we are going to use two models of mechanics. So the one is a particle, a particle in Chinese maybe is a lead, or actually we have a terminology, we call that 质点. So a particle is a material body precise in mass, the shape and the size of which can be neglected in investigating its motion, right? So you guys can think about that a particle is the ideal model, it is a model. So I can give you an example. Do you guys have the concept of the size comparison between the sun and the earth? Do you guys have that information? So maybe I can tell you. So maybe here we just use a big circular shape to mean this is the sun, right? It is the sun, the sun. But compared to the sun, our Earth, although it's very big, it's very, very small compared to the sun. So let me give you a very interesting example. If we have a very delicious watermelon, do you guys know what is watermelon? 西瓜, right? It is very delicious. If we have a watermelon, and we just use a very sharp pen to point a point on this watermelon, then you can think about that. This watermelon maybe is the size of the sun, but this point on this watermelon is just the size of our Earth, So actually, our Earth have elliptical uh, 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 trajectory. Maybe here is our Earth, right? This is Earth. EARTH. So every 24 hours, it will rotate around itself one revolution, and every 365 days, it will along this elliptical orbit around the sun. So we have 4 seasons, spring, how to say, 春夏秋冬, autumn, and 春夏秋冬. We have 4 seasons, right? 春夏秋冬. Spring, summer, autumn. How to see the dong? I don't know what. How should we said this? The fourth season of a year. Spring, summer, autumn. How to see this? What? I forget that. So I mean, in this, because the size of Earth is too small compared to the sun. So when we are investigating its movement around the sun, we can just look at the Earth to be a particle, right? So in Chinese, we call that 质点. So that means it only has some mass, but its size or shape have very, very tiny influence to the result, what we are investigating in, right? So this is a particle. Another is a system of particles. So that means a system of particles means a lot of particles. So if this is 质点, we call that 质点系, you know, 质点系. So a system of particles is the collection of material points in which the position and the motion of each particle of the system depend on the position and motion of all the other particles. Then we have another important thing. You guys should know that every, every every rigid body is a system of particles. No, a system of particles. So you guys can think about that. So we can look at a rigid body because a rigid body may have some mass, may have some shape and size. So we can think about that. There is a lot of particles or 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 because of them constitute this rigid body. Any two particles on this rigid body will never change its position because rigid body actually is ideal model, right? Because it don't have any deflection or deformation, although all kind of more force acting on it, right? So every rigid body is a system of particles, right? So you guys should know these two models of mechanics. So when we will use this particle model and when we will use the system of particles, totally according to the problem we are investigating. So once again, if we are investigating the motion of the Earth along or around the sun, then we can just look at the Earth to be a particle is enough, right? But when we are studying some normal engineering problem, and engineering problem, then we should treat it. We should treat all the body system as a system of particles. System of particles. So I hope you guys have a basic impression here, before we learn something, right? And let me erase all I have right on here. A rigid body, actually, uh, uh, so a rigid body is a special system of particles composed of a large number of particles. The distance between any 2 points of which remains the same during the whole motion. It is also called to be a non-deformable system, 非变形系统. You see? So the first, second model and a rigid body actually is a system of particles. Actually, we will investigate get a lot of mechanism, so actually if we have a lot of rigid bodies to constitute a body system, actually it is a kind of mechanism. Then that mechanism also is a special system of particles. So please, you guys should know that. We will continue to introduce this. And let's see, system of free particles. A system in which the motion of each particle is not restricted by any constraint. That means it is a system of free particles in which the motion of each particle is not restricted by any constraint. Another is a system of non-free particles. This is very realism, right? So actually we don't have this system of free particles, I think. Maybe some kind of this system can be treated as system of free particles at some situation, right? At some situation. And so system of non-free particles refers to a system in which the motion of particle is restricted by constraints. And a system of particles is the most general abstract model. You know, 质点系, we call that 质点系. A system of particles is the most general abstract model of mechanics, including rigid bodies, elastic bodies, and fluid. But here we will not study this kind of problems, right? Maybe we will only focus on or mainly focus on rigid bodies, right? And let's see the classification of dynamics. We have one is particle dynamics. We call that 质点动力学. So you guys can try to try to think about the logic of this whole dynamics, because we will start to learn the particles dynamics. Then we'll study a lot of particles. That means 质点系动力学. So this is one particles dynamics. Then that dynamics of a system of particles, that is 质点系动力学. And our rigid body actually is the special case of 质点系, right? And then a lot of rigid body can constitute some 物体系统, right? 物体系统. So here 钢体 means rigid body, rigid body. And here 物体系统 means mechanism, you know, actually mechanism. Maybe I can draw a mechanism quickly to you guys here. You can find actually we have learned this kind of things, right? You remember? Actually, this is kind of this omega O A B, right? So when OA have omega with constant velocity omega around the point O with this direction, and there is a force along from A to B, then this ladder will have a translational movement around this dashed line trajectory. So we call that actually, this is the typical mechanism. You see, so one of the linkage is the rigid body, and they can be some type of constraint constitute a mechanism. Then this ladder may be useful to do something we are needed on our engineering life. You see, actually this is a whole topic, a whole path of this third part. We start to learn some particles dynamics, then we are going to study the dynamics of a system of particles. Then this knowledge can be used into rigid body and rigid bodies, or system of rigid body, or mechanisms, right? So that's the brief introduction of this part. So today we are going to learn chapter 11, actually the differential equation of motion of a particle. So actually this is what we will start to learn, particles dynamics. It's quite easy. We will discuss some typical example together. So we'll talk about two topics from two sections. So one is the differential equations of motion of a particle. The differential equations of motion of a particle. The second is the two types of problems of particle dynamics. Let's say first the differential. Actually, we just use this. Maybe you guys know this. Maybe I can write as in many cases I like to write as this F equal M A. So if we write as this vector form, 矢量的形式, do you guys still remember what we have learned from the middle part of this course? So we have coordinate, right? X, Y, and Z. This is our SCS, stationary coordinate system. So if we know some point along some trajectory here, so we can link OM. Do you still remember? We have vector OM. Let's say it's R, it's a position vector of this point M. So if we look at this point M, a particle which only have mass, we do not consider its size. So, you know, actually dr dt equal v, right? And d squared r dt squared equal a. And this is the second law of Newton's. So it tells us the relationship between the acceleration and the force. So this is why we have this vector form. D squared r over dt squared equal f. So in this formula, actually r describes the equation of motion of a particle. Actually, it's the position vector. We have learned that before, right? Have learned that. And since this one is the equator, vector equation. So we can use this projection it onto 3 axes. So we have m d squared x dt squared equal x. So that means m a x equal sigma fx. So do you guys still remember? Actually, we have learned this from statics. So from the first part of this course, when we study a body system and we know it's in the station of equilibrium, especially the plane problem. You know, do you guys still remember? We have 3 equations to study the state of equilibrium of body system. Actually, we have sigma fx equals 0. Do you guys still remember? We have sigma fy equals 0. And we can arbitrarily select a point and all the force of this body system, its moment to the same point, its sum also should equal 0. That's why the whole body system is in the state of equilibrium. So when we are when we have the information that this body system not in the state of equilibrium again, it has some kind of motion. So we will rewrite as this not 0. It should equal max. It equal may here. What should be this? Because this is the moment. So here we should equal. We will learn this inertial of mass, 转动惯量 times alpha, which is angular acceleration. So these 2 expressions will consider the relationship with force and translational acceleration. And this moment, this expression will give the relationship between the our principal moment, 主句, or the resultant moment to the angular acceleration of the same body system. See? That's why dynamics will be the third part to be learned, because we need the information of what we have learned from statics and from the kinematics, right? So Because of the same reason, we can write as MAY equal sigma FY, right? We also can, I don't know why this guy also here. Okay, so here we also can write as this. So here we can write MAZ equal sigma FZ. So here we are talking about the differential equation of a particle because the particle, we call that 质点 only have mass. We do not consider its shape. So you guys should know that a particle only have three kind of motion. That is all the motion along the three axes, maybe along X, along Y, and along Z. So if we are talking about a rotation of a particle, is meaningless, you know? So you can think about if you said there is a very tiny point, its rotation have some kind of rotation, so it's meaningless, right? It's meaningless, 没有意义 because we don't consider its size. So its rotation maybe have no effect of our final result. So I have mentioned when we can look at the object to be a particle totally according to the problem we are investigating in, right? So here, for a particle, actually we only use these three versions, right? And in this formula, this actually x equal xt and our ax actually equal x double dot t. See, that's what we have learned from the kinematics, right? So the same reason ay equal yt double dot and az equal zt double dot, right? Another is the natural form. Do you guys still remember we have a natural coordinate system? So I will review that again. So if we know a point, here we can talk about that point is a particle will along a fixed trajectory. So before we started the motion of this point, we know its trajectory or path already, right? We know it's past our trajectory already, this is point M. So it's very useful or very simple. We select a reference point and we just use this because it's always along this path. So maybe this time it moved to this position. So from here to here, we have a curved length up here. So we have its natural form is S equal maybe ST, and its velocity will only equal S dot tau direction. So actually we only need to do the tangent line here. That is tau direction. And its velocity will always along this direction, right? So here we can draw its v, and this magnitude will equal s dot. Then I will change another color to review this. So when we are talking about its acceleration, when we are talking about its acceleration, then we know we should give another direction, which is normal line direction. It will point to the curved center, 曲率中心, right? We call that n direction, normal line direction. So its velocity will always equal what? A t or a tau along tau direction and a n along n direction. And we have our AT actually equal S double dot, right? S double dot actually is d squared as dt squared. It only gives the change speed of the its magnitude of the velocity, so we have this. It should f tau, right? And we also have an is always equal v squared over rho, and rho is the 曲率半径 here, right? So, we have, we can draw a tau. Maybe we have a tau here. We have a n here. So from the second law of Newton's, so we have man, right? So it will have force along n direction. It will have force along tau direction. Since we know at b direction, because we have because our b direction always equal tau cross plus n, right? So with right-hand rule, we can find actually b direction will along this direction, because acceleration will never have opponent along this direction. So this will be always 0. So if the force acting on this particle, it have component along b direction, then its resultant, or we can say the principal force, its projection onto b direction will always be 0. Why? Because non-zero component along b direction. That's what we learned, right? That's what we learned, the so-called natural coordinate system. So in these formulas, in this formulae, S equal st describe the motion of a particle in terms of the arc coordinate. We call that 自然坐标系, right? We call that 自然坐标系, and of which f tau, fn, and fb are respectively the projections of the resultant force, So if I give you another conclusion, if we have a particle here, and we have a lot of force acting on the same particle here, so you guys will find all this force will constitute a concurrent force system. Concurrent. And you guys, you remember what we have learned, what is the concurrent force system? Force system. We call that 会交力系, right? Because this concurrent force system, we can use the parallelogram rule, right? It always can be replaced by only one principal force. That is resultant force of this whole concurrent force system, right? So we call that 主使 principal vector, right? So we have Fr. We can project this force F actually the Fr. All the forces acting on the same point, it can be replaced by a only resultant force Fr. And we can do the projection onto tau direction, onto n direction, and onto b direction, which is f tau, fn, and fb here. No? And besides these three forms, differential equation of, besides these three forms, differential equations of a motion of a particle may be represented in the forms of polar and other coordinates. Then we are not talking about the polar and other coordinates here. Maybe sometimes you guys will encounter that kind of expression, but it's easy to understand. And applying the equations, we can solve two types of problems of particle dynamics. Actually, that's we call them two types of problems. It's very easy to understand, you know. So I can show you guys like this. So since we know F equal F A, so maybe if we know F, if F is known, then we can find A actually equal F over M. You see? So that is the kind of problems. So this is the first tab. The second is if we know A, so we can find actually F equal M times A. So this is the second type of problems. So since we can use F over M can find A, so we can do two times of integral calculation. Then we can find V and S. And since we can use this, so if we only know S, we can do S dot equal V and S double dot equal V dot equal A. Then we can use M times A to find force. That means the two types of problems we are going to talk about. So let's say that's the two types of problem of particle dynamics. 质点动力学 Particle means 质点 dynamics with 动力学 So that is 质点动力学 The first is knowing the motion of a particle. That means maybe we know S, V, A, right? This is displacement, this is velocity, and this is acceleration. Let us determine the force acting on it. So it's easy, right? We just use F equal M times A. We can finish the calculation. The second is knowing the forces acting on the particle, determine the motion of the particle. So once again, we can use A equal F over M. Then we can use V equal FA dt and S equal integral calculation V dt to find the motion. So the first is knowing the motion to determine the force acting on it. The second is knowing the forces acting on the particle. Let us determine the motion of the particle. You see, it's quite easy, huh? But when we are encountering different real problem, we should treat it very carefully. So maybe we will have impression to these two types of problems with some examples, right? I hope you guys can understand that. So let's see the first example. Let's see. We have a breed crane. A bridge crane in China we call that 桥式起重机。桥式起重机 Maybe we also have another name. We call that 天车 because it presents the overhead. Maybe all the workers are on the ground. Let's say this is the ground. All the workers like us, we are just standing on the ground. So it's overhead direction. So maybe we call that 天车, right? So a bridge crane suspending a load, suspending with a steel rope, right? Whose weight is G. Let's see, it's G. So G means is gravitational force, moves uniformly, right? At is velocity, its velocity is, I think it's v, right? The distance from the center of the load to the point of suspension is L. If the crane suddenly breaks, actually it means uh, if you guys can look from up along downward direction. So actually this at first let's see this. This vehicle, it have uniform velocity. The distance from the center of the load to the point is L. If the crane suddenly breaks, the load will swing forward. Why? We call that inertial. 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 I'm not sure if I write this English word correct, but in Chinese we call that 惯性, right? So particle of things always try to keep its original state of motion. That means inertial. Try to keep its original motion pattern, right? Because this suspending load and this vehicle has uniform velocity v zero, but because some reason this vehicle or this crane suddenly stopped here, so it will not move again, but this this load will try to keep its original motion with zero, so it will swing around this point with this phi, right? So that's why the load will swing forward due to the inertia. I don't find the word here. I try to write it myself, inertia. I'm very happy that I read the correct word, right? Inertia. We Chinese call that 惯性. That means the characteristic of ability to keep or try to keep its original motion, right? So let us determine the maximum tension in the steel cable. So we call that this is the steel rope or steel cable, right? So you guys can find its analysis precise. So, so you should pay attention to the its process of analysis. So one is this: choose the load as the object to be investigated. So one is 选择研究对象, right? We choose the load. Here's a green box, maybe, as the object to be investigated. Do you guys still remember when we do the force analysis, we always should draw the FBD, free body diagram. We just imagine that we free some object from the body system. We use all the body is force acting onto the body, right? That is the free body diagram when we do the force analysis. So here we choose the load as the object to be investigated because it has this kind of motion. So if we are sitting on this vehicle, we will find actually it swing like this, right? So the analysis of force is shown in the diagram because it's more like that the point, also the center of the mass, right? It swing along this circular trajectory or circular path, and its radius is L, right? So let's say if we swing from the vertical position to this position with this intersect angle is phi, right? So its force will just is this gravitational force G and this tension force because of the steel cable. And our task is determine the maximum tension in the steel cable. So you get confined, actually we know along this direction is V. Analysis motion, the load swings along a circular with center O and the radius L, right? So we will try to find its acceleration first, then we can use the second law of Newton's along tau direction and n direction. You see, this is, can you guys see? This is the tau direction of the natural coordinate system, and this is n direction, right? So we can find. So with the differential equation of motion in natural form, so we have ma tau should equal sigma f tau. And here, actually, we only know its weight. So m equal g over gravity of the Earth times dv dt. Actually, dv dt is the acceleration along tau direction, right? It will minus what? So you can think that if I draw an AD line here, so because this is perpendicular to this, all these are two vertical lines, so we have a phi. Then we have sigma f tau equal, so this is n direction, this is tau direction. So g times cosine phi will be components along n direction, and g times sine phi will along the tau direction and along the negative direction of tau. So we have minus g sine phi, right? And so we have this. We also have MAN equals sigma Fn. Actually, our sigma Fn is along this. So we have T minus G cosine phi, right? And this one should equal ma tau. And this one should equal MAN. So we should have a tau and an, then we can find T, right? So from this second expression, can you guys can find this? We find this T, right? We find this T because we have along the n direction, its acceleration an should equal v squared over rho, right? Maybe I should write here. So we have g over g, actually is m, and this v squared over l is a n equal t minus g cosine phi. So we can get this g, right, cosine phi over v squared gl, right? So because all these things are constant, the maximum of t are totally according up to this cosine phi. We know when phi equals 0, cosine phi has the maximum value with just 1. So when phi equals 0, we have t equal t max, and t max just equal this. See? That's how we use the differential equation of a particle and find the answer. So can you guys understand this problem? Maybe we can look at another example. So let me read its introduction of this. You guys can just look at the picture. A stuffing mechanism is employed to stuff of the stuff material in a coal mine, right? The stuffing material has to be thrown. I think that is a kind of mechanism which will throw some bodies, right? The stuffing material has to be thrown to the position A. We will throw to the position A of the roof board at a distance S equal 5 meters, right? And H equal 1.5 meters are shown in the figure. So determine one, the initial velocity of the stuffing material with 0. Actually, the second is the angle alpha 0. That's the initial velocity mixed with the horizon. So I think we can analyze this picture here. This V0, our final destination is we thrown this body on the what? On the roof board, right? But this V0 with this intersect angle alpha 0 will have two components. So Vx along horizontal line will V0 times cosine alpha. And Vy equal V0 times sine alpha. So when a body is thrown uh, 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 onto the air, so at the vertical direction, so this only have one external force is mg, so it will accelerated movement, and this h will determine the time of the t when it can reach the highest position, right? Let me illustrate this. This h, I'm sorry, this Vy its value because of this h is our required position h and s, right? This Vi, its magnitude will totally determine the time t when this stuffing can reach the highest position, right? And this Vx, it can totally determine what horizontal distance it can reach until this t. That means h sh equal this Vx times t, and this t will just equal Vy over g, right? Because it constituent deaccelerated motion because of this m over m, mg over m is acceleration always be g, right? So use these two expressions, we can find the final result. I hope you guys can understand what I'm talking about, right? So let's see the answer. So our solution is, so first, we choose the stuffing material M to be investigated. So it is a particle, right? So when T equals 0, so X 0 equals 0, Y 0 equals 0. So Vox is the initial velocity V0 is X component, Voy is Y component. And when M try to reach to the position A, our X should be S, right? And the Y should be H. Then can finish its requirement, right? So Vx and Vy. Then we write the differential equations of the motion of a particle in terms of Cartesian rectangular coordinates and perform its integration, So m dvx dt, that is ax, is always 0, This particle, there are no external forces along horizontal line, along x direction. So this one will always be 0. So we have this. We have dx dt must be a constant. But we don't know that either until now. And secondly, the m dvy dt should be minus mg, because our positive direction here, and g along mg along this direction. So that's why we have this, right? We have this minus direction because mg is direction in the opposite to this positive y direction. Then we have this. So minus gt plus another constant c second. So if we finish find c1 and c second, then we will finish this calculation. Then we can use this. We can integral calculation from this to this. So x should equal this one plus this one. And y should equal this one plus this one. So we have C1, C second, C third, C4. We have four unknown parameters. Then we can find this and this. So when t equals 0, we have x0, y0. When t equals t, we have this and this, this and this. Then we can use all this information to find C1, C3, C2, and C4, right? That's how we find its final result. You just need substituting the initial conditions into this expression, and we can obtain this. No? Then we can find the equation of motion, the path is given by this, right? So this is y and this is x, right? Because the projection of the velocity at the height points of 0, y0, we obtain this dy dt. You see? Can you see this? Actually, I just write this before we showed this page at that page. You know, that's how we write with zero sine alpha. I think this problem is quite easy for you guys. You can totally understand that, right? I think that's all for today. You can review this by yourself again. And today we don't have homework. So that's all for today. Bye bye. 下课吧，同学们。
OK，老师。
Okay, I'll see you guys next time. 下次见啊，拜拜。
Bye.
拜拜。